So we've talked about the natural log a bunch, and we've talked about its definition over and over, that it's defined as the definite integral from 1 to x of 1 over t dt. So by the second fundamental theorem of calculus, its derivative is equal to 1 over x. Right? That's the definition. This is an antiderivative, so therefore its derivative returns the original function. That's second fundamental theorem of calculus. So that's good, great, and wonderful, but what happens in the case where we have a differentiable function of x, u? So what's the derivative of a natural log of something that's not just x? Well, we use the chain rule. So we take the derivative as if it were an x, so you get like a 1 over whatever's there, and then you chain the derivative of that whatever. So it's 1 over whatever times the derivative of whatever. So often it's written in a compact notation of u prime over u, but that's just, again, it's the same thing. Now we have a more interesting result, which is that if you do the same thing for the absolute value, if the natural log of the absolute value, you get this derivative. This is really useful because, if you remember, the domain of the natural log is positive numbers, right? It's from 0 to infinity. But if you take the natural log of the absolute value of something, you now can expand the domain to all the real numbers except 0. It's still not defined at 0, but it's defined at every other real number. So you can take a natural log of negative numbers and of positive numbers, just not 0. But you might think, oh, that could complicate things. Well, it turns out for derivatives, it really doesn't. You get the same exact derivative as if you didn't have an absolute value. So when dealing with these types of things, it saves you an extra step of having to check yourself.